Giovanni Marinaro, I'm a postdoc from King Abdullah University of Science and Technology. So Marco Marengo is the master student who helped me for this work. I'm talking about flexible temperature and flow sensor from laser-induced graphene. So I will talk about my motivation, the fabrication and the characterization of laser-induced graphene, and two main applications. This material used as flow and temperature sensor. At the end, some conclusions. So smart living requires nowadays sensor that should be multifunctional, flexible, simple to control, identifiable. They should communicate each other in an Internet of Things where the things are the sensors, interconnectable, cheap, and biocompatible, possibly. So laser-induced graphene is one of the material we can use as a smart living sensor. Why? It's thermally stable, it's electrically conductive, and it's mechanically flexible. If you see here, for example, we can reach temperature up to 600 degrees, and it doesn't change so much the weight percentage, 3–4%. It is electrically conductive. You can change the main parameter of fabrication and get in a range of 10 ohms this resistance, and also if you have a thick layer of graphene, you are also changing the resistance. And this is the graphene laser scribed on a polymeric material. It's a thin film. So it's flexible. It's the so-called Capton. So it's also corrosive resistant and biocompatible, as you can see from this reference. I want to show you an example of the state of the art nowadays about this fabrication method. Here it's made on PDMS, so you can twist and bend the sensor. And these are the material used for flexible sensor nowadays. I'm choosing graphene because of this outstanding value. The gauge factor can vary between 2 and 112. The percentage of deformation is 7. This is a behavior as negative coefficient temperature coefficient. So the behavior is that it increases if you increase the it decreases if you increase the temperature. So the working principle of the two applications I want to show you is on the left as deflection sensor. Just to apply a normal force on this cantilever, you will have this pattern of force, tensile on the up and a compressive status of forces below. And the piezoresistive effect is given by the gauge factor I was talking to you before. And as a thermistor, the physical behavior is explained simply by the thermal agitation. You increase the temperature, so more charge carrier will move into the conduction band. And this is equivalent circuit I will use. So it's a very simple circuit. You can put your sensor here and just apply a current, and you will measure the difference in voltage. So I want to show you now the very quick method to make laser-induced graphene. So as you can see, it's a raster scan process, left and right, and it's simple, fast, and it doesn't cost so much, maybe less than $1 USD dollar. And how does it happen? So it's a photothermal conversion of polyamide to graphene. So the laser is focused on a very narrow spot, and the temperature there is very locally high. So it burns the polymer, and all the chemical bonds will be broken, and all for example, the CO bonds and CH bonds will be broken, the chemical species will become volatile and they will evaporate. This is the speed I used and the main parameter of the fabrication. And these are the two examples. This pattern and that one are made like a meandra. So we will bend this sensor on one case, and then we will measure the resistance as a thermistor. And this is the characterization of the laser-induced graphene. We can get a thickness of roughly 75 micrometer, and it's obtained on a PI. We can buy it from a company, and it was originally 125 micrometer thick. As you can see from the top view, this material is extremely porous, so it can also be used as a gas sensor, for example, by exploiting the interaction between the carbon and the other molecules. And here is the signature that we are talking about graphene. So these are the three main peaks. In particular, the first and second generation harmonic of 2D. And in such a case, you can see that it's like a lamella structure folding each other. And this is the behavior as bidirectional deflection. This was the first test. So at A static 1, 2, 3, it comes to the resting position. There is not much relevant hysteresis. I mean, it's quite negligible. And then if you start to bend it in B, C, D cases, you can see that the voltage will increase. And this is the opposite. So when you bend up the sensor, and so you can measure different velocities from different directions. And this is the behavior in tapping mode. So the response is quite fast. And what is very interesting is that the low consumption. We applied 1 microampere, and we can see that the consumption is very low. So the second test was to see the behavior of the sensor in liquid. We used water. So this is the water is coming in from here and goes out from this cross section. And the sensor is put through a slit inside a PMA chamber. We put some PDMS, spin-coated PDMS on top in order to avoid short circuit of the graphene. And these are the different speed we used by pump. And as you can see, there is some perturbation due to the laminar flow that goes to the top of the sensor. But it can discriminate different velocity. For instance, the moving average of the resistance can allow how to measure these different speeds. And the resolution is, the sensitivity here is 6 ohms over meter per second over -1. And here is the result as thermistor. So you can see in this area here that the temperature coefficient is roughly 4 ohms over Celsius degrees. Typically, commercially, we have this value here, but for our purposes, it's still okay. And also here, the parameters about current and power are still very good. So in conclusion, we can say that our sensors are very low power consumable, are simple for measurements, they have just a resistive behavior, and you can tune shape, size, and thickness as you think of. It's very low, light. The sensor is deformable and can be used as transparent polyamide. And what is very important for us is the multifunctionality, because we work on the Red Sea and we want to measure several parameters, physical parameters. So we want to implement, for example, in the future, an interdigitated sensor to measure the salinity by exploiting the double layer effect. And we will think about other sensors in the future. I would like to thank all my group members, in particular Marco Marengo, as I told you before, and my advisor Jürgen Kosel. And I would like to thank you for your attention.